Welcome to Retaining Structure series. This will be lecture 1. My name is Liban Afi and I'm the founder at soilstructure.com, which is soil structure software. Okay, we specialize in geotechnical engineering software and retaining structures or substructural software. So let's talk today about earth pressures. The photograph on the left, you can see a concrete worker doing the vibration in the concrete and pour in the stem wall. The reinforcement you can see is coming out. The footing has already been poured, and this is a residential project. And on the right hand side is a segmental retaining wall, and you can see the drain weep hole coming out. So at the end of this class you should be able to understand the active earth pressure behind these retaining walls, as well as at rest earth pressure and passive resistance. So active earth pressure, what is it? It applies to retaining walls that are able to rotate at the top, and we denote the active earth pressure as K sub A, and it purely comes from the backfill soils and is only a function of soil's friction angle phi. These are typical earth pressure values, and these are granular soils. Here is a range of soil friction angles. Here is their consistency, whether they're loose, medium dense, or dense. These are the typical moist unit weights of the soil. And here is the Ka, or the active earth pressure coefficient. For gravelly soils, it's from 0.21 to 0.35. The higher the number, that means the looser the soil. And the smaller the earth pressure coefficient, it means denser soil. And the Ka gamma, this is the equivalent fluid unit weight, and it applies only to level backfill. And it's 27 PCF if the soil friction angle is 41 degrees and the soil unit weight is 130 degrees, and so on. So if this is the wall that we're going to design, the active earth pressure comes from the backfill side, and the passive resistance provides resistance to the overturning that's caused by the active earth pressure. And if the wall was to fail, it will fail over this plane, which is approximately 60 degrees from the horizontal, and at the passive it will fail at this angle. So how do we calculate the active earth pressure? If we have a wall that's 10 foot high, Ka is tan squared 45 minus phi over 2. If the friction angle is 30 degrees, so the Ka will be tan squared 45 minus 30 over 2, and we should get 0.333. And the lateral stress, this is the base of the wall. The horizontal stress is Ka times the vertical stress. The vertical stress is gamma H. It's 120 unit weight of soil times the height. So that's 1200 times Ka, it's 0.33 of that, so it's approximately 400 PSF. That's the lateral stress. Well, what's the earth pressure? The earth pressure P is the area of the triangle. So it's 1/2 times the base times the height. So it's 1/2 times the 400 times the 10, so it's almost 2,000 pound per foot, or it's 2 kips per foot. So every foot into the page, the force that backfill force that the wall experiences is 2,000 pounds per foot. What is the passive earth resistance? Note that I don't call it pressure, it's a resistance. This applies to provide a stabilizing resistance to the retaining wall. And the coefficient for passive is noted as K sub P, and it comes from the buried soils. So if the retaining wall footing was buried 5 feet deep, then the K sub P is tan squared 45 plus phi over 2. And if phi is 30 degrees, so it will be tan squared 45 plus 30 over 2, and K sub P will be 3.00. And what is the passive resistance? it acts at h over 3, and it's the area of the triangle. So it's 1/2 gamma h squared kp. So that's 0.5 times 120 for gamma times 5 feet squared, which is the buried height, times the k sub p, which is 3.0, and that gives us 4,500 pounds per foot. Now let's compare what is active, what is passive, and what's at rest. So let's start with at rest. If the wall was not to experience any movement, then the wall is supposed to be in at rest condition. So the coefficient is K0 1 minus sine phi. That's the at rest earth pressure. We're going to come into that in a minute. But we've talked about active. Active means the soil barely moves. So it does move, but not that much. So then that's called active. That means the wall is moving away from the backfill. Passive requires a much larger movement, and that means the wall is going into the backfill. Okay, so at rest is no movement. Active is the wall is moving away from the backfill, and passive, the wall is moving into the backfill. So what's at rest pressure? It applies to basement walls. It's misnomer to say, I don't want the wall to move, so I'm going to design it for at rest earth pressure. It doesn't work like that. At rest earth pressure only applies if you have a strut force or some kind of a prop near the top of the wall. Okay. Then the at rest pressure coefficient is noted as K sub naught, and it's higher than the active pressure but less than the passive resistance. So if you go back to the last diagram, here is at rest. It's higher than the active pressure, but it's less than the passive resistance. At rest, it's called K0. It's 1 minus sine phi. This is assuming the soils are normally consolidated. So let's change the phi from 30 to 32. So 1 minus sine 32 is 0.53, and the thrust for at rest condition is 1/2 K0 gamma h squared. It's the area of the triangle. So it's 1/2 times 0.53 times 120 times this wall now is only 7 feet. So 7 foot squared. So we get 1558 pounds per foot on the wall. So this phi angle that we talked about, where do we get it? So when we go to a job site, we take soil samples, and from there it's called undisturbed soil samples in a ring, and we test it in a direct shear test machine, and then we get two envelopes. We get the upper level envelope, which is the maximum strength the soil would see. That's called peak strength, and it's right here, peak. And then we test it in the lower level boundary where the soil strength would not be any lower than that, and that's called the ultimate strength. So the peak strength is 87.5 degrees for this particular soil, and cohesion is the y-intercept. It's 166 psf. Okay, so active earth pressure applies to all these retaining walls. It's trying to destabilize it. So this is a concrete retaining wall. This is CMU, but it's tiered retaining wall or cascading retaining wall. This is a block or a CMU wall. This is a geogrid retaining wall. This is an I-beam or a soldier beam retaining wall with concrete lagging. And this is a block retaining wall, but it's also a tiered retaining wall. So active pressure applies to all of these retaining walls in the backfill side. This particular one has a V-pole. And passive resistance, you cannot see it, it's buried. So it's providing resistance in the footing, in the buried footing portion. The same thing here, the same thing here, the same thing here. But here, this will be embedded retaining wall or a soldier beam wall, and the embedment depth is usually 1.3 times the retained height, and that's where the passive resistance is applied. And this would have it under the buried footing section. At rest earth pressure applies to basement walls. Right now there is no pressure because the wall is not backfilled, but once the wall is backfilled and the braces, the wood joists are connected to the top, then the wall cannot move. So it will be under the at-rest earth pressure. I thank you very much for joining me in this class and hope to see you in lecture 2. Bye-bye.